of a frequency distribution. So we looked at frequency distributions where we had the actual data values listed, but in this case we're looking at something that's grouped. Grouped data presents us with a little bit of a problem because unless we have access to the original data set, we have no idea what the actual data values are. We only know the range of values they fall in and how many are in that range of values. So for example, without looking at the actual data values here, we know that there are 3 data values in the class 235 to 272, but we have no idea what they are. They could all be 235. Or perhaps they could be spread out a little bit, like say 242, or 249, or 271. Or perhaps 253, 254, 264. We have no idea which of these it could be, and there's any of 100 different other combinations that could happen here. Actually far more than that. So we don't actually know what values they are. So we get around that by using the midpoint of the class as a representative value. Now the midpoint of classes, that's an older topic. We take the lower and upper limits, add them, and divide by 2. Essentially finding the mean of the lower and upper limits. In this case, that would give us 507 over 2, which gives us 253.5. That's the midpoint of the class. So the idea is, since we don't know what the first value is, we don't know what the second, we don't know what the third is, we're going to treat all 3 of them as if they were 253.5. Now obviously none of them are 253.5 since all of the data values in this were whole numbers. But let's see how it stacks up to these few examples that I gave. Let's say the actual data values were each 235. Well, in that case, 253.5 is overestimating the value of each one. Now, that's possible, of course, but that's, I don't know, that would seem kind of strange to have all 3 values be 235. Totally possible, but probably unusual. Now take a look at some of the others. Like this, the second one. 253.5 is overestimating 242. Not by terribly much, but by a bit. It's also overestimating 249, but by much less. However, it is very much underestimating 271. So the 253.5 is sort of striking a balance. It overestimates some values, it may underestimate others, but overall, it actually comes out to be, well, honestly, not all that far off. Even in a case such as this third one, it does slightly overestimate and slightly underestimate. Okay, and underestimates more. But my point is that since we don't know which situation we could be looking at, this seems to strike a pretty good balance because it has an equal chance of overestimating or underestimating the actual data values. And when we apply that not just to the one class, but to all of the classes, okay, let's say this was the real case and the 253.5 is an overestimation here. For all we know, in a different class, the midpoint may be underestimating all of them. So the same way that there's a really good chance the midpoint is offering a decent estimation in any single class, using the midpoints throughout the frequency distribution, again, offers a good chance of overestimating or underestimating with equal probability. Now, that may sound all rather confusing. Let's take a look at it in practice. So, we calculate the midpoint of each class. Now, I'm going to take the liberty of going ahead a little bit here and saying we actually used this frequency distribution and found the midpoints for them at an earlier lesson in the course, namely the section on frequency distributions. So we can kind of skip just a little bit ahead here and fill this in a little faster. Certainly feel free to do these calculations all yourself. So, what we're now looking at is actually very much like the example in the PowerPoint where we had the three data values, 3, 5, and 6, and their frequencies. At this point, these classes are really no longer important to the calculation of the mean. We're now going to use only these as our data values. So at this point, it becomes the same calculation that we saw in the PowerPoint, namely that we need to take each x value, each midpoint, and multiply it by the number of times that data value occurs. Now again, we're supposing here. There are 10 values in there, but it's kind of hard to add up all the 10 values when we don't know what any of them are. So we're pretending each one of them is 101.5, understanding that again, some of the actual data values may be smaller than 101.5, some of them may be larger. So this strikes a decent balance. So we do 101.5 times 10, which gives us 1015. We do 139.5 times 20. Certainly feel free to use a calculator here. I know for some of these I'm going to. Some of them are easy enough, like multiplying by 10. Some of them, no, a little less so. I'm just going to run through a calculator real quick and double check a few of these. Make sure that we have the right values before we proceed. Looking good so far. Excellent. Okay. All of these values are correct, so the last step then, or excuse me, the next to last step, is to add all of these up. What we're doing now is adding up the x times f. We're summing up all of the x times f's. Again, calculator. That comes out to be 8,001. Now, we're not quite done. That is the sum of the x times f, but we do have another step to do, and that is to divide by the sample size. Now, the sample size comes from adding up the frequencies, and that's 50. So, I'm going to erase some of this to make some room. And the mean of this frequency distribution is the sum of the x times f's over the sample size. So 8,001 over 50 gives us 160.02. Now, that's only 2 decimal places, so at the moment I'm inclined to keep them, but typically we would round to a single decimal place, which in this case would be 160.0, or just 160. Now, how good is that? Is that even close? Is that even remotely close to what this should be? Well, as it turns out, again, we did this problem earlier in the semester. This was the drive-through data. So we have that file available to us with the raw data. This is not typically the case, but since we happen to have it here, let's try out this new method and see if it actually is giving us what it's supposed to give us. Now, remembering again, we don't typically have access to this if we're just using the frequency distribution. As it turns out, the sum of the x values in the raw data is actually 8,012. Look at how close that is. This was the sum that we got, assuming every data value to be the midpoint of its class. This is the actual sum of the actual individual data values. When you consider that we took 50 data values and pretended that each of them was a class midpoint, and it added up to a total of 8,000, the fact that we were only off by 11 is remarkable. That is amazingly accurate. Now, that's not always the case, but in most situations, the sum of the x times f using the midpoints will be very, very close to the sum of the actual raw data values. That makes this a decent alternative, and certainly much quicker than having to go through 50 of these numbers. Remember, they ranged from 83 to over 300. Having to type in all 50 of those numbers into a calculator and add them together to get 8,012 is a little ridiculous. So I'm going to add something to the x bars here to kind of make a little bit of a distinction between them. I'm going to call this the x bar of the grouped data. And here, I'm going to call this x bar of the raw data. And they actually are going to produce a remarkably close value. This comes out to be 160.24, or approximately 160.2. That's amazing that in pretending that we knew what all 50 values were, as opposed to actually knowing what all 50 values were, we came up with amazingly similar results. Now, obviously, if you have access to the raw data and a computer, it can be very quick to get this value, or even just directly to the mean of the data set. But there are many times where we don't see the actual data, we only see the summarization of it in the frequency distribution, which means that we now have a method to find a very reliable estimate of the sample mean without ever having to actually see the data values themselves. Now, admittedly, it's not always that good, but it's never very much further off either. the mean of grouped data is surprisingly accurate to the mean of the raw data. And that makes this a very viable and quicker alternative in many cases.